Okay, so in the previous lecture we had discussed about what is the T-cyclic subspace, right? So let us quickly recall what we had defined T-cyclic subspace of a certain vector alpha. So quick recall. So if you are given a, let's say a finite dimensional vector space, for example, let V be a finite dimensional vector space and T is a linear operator defined on it. Okay, let alpha be a vector in V. Okay, then the T-cyclic subspace generated by alpha is the term we use. It's the subspace denoted as Z alpha T, which consists of all vectors of the form GT of alpha, such that G is a polynomial. Obviously over the underlying fields, but we have not considered the underlying field as a notation here. So let us just write it's a polynomial. Okay? Yeah. So we had discussed enough examples regarding this. Right. So let us quickly define one more important aspect of today's lecture, which is the concept of a T-annihilator of a vector. Definition: let alpha be a vector in V. The T-annihilator of alpha, it's typically the ideal denoted as M alpha T in Fx, which consisting of all polynomials G such that G of T of alpha is equal to 0. Okay. Obviously, we are specifying it to be a T-annihilator. So T is some linear operator defined on P, where T is a linear operator defined on P. Right? Now it's obvious why this is an ideal. So because if you choose any two elements from this set, then the difference of them will also behave analogously. And if you multiply that with any other polynomial, then the product will also go to 0 for the vector alpha. Right? So what I'm trying to say is that if you choose two elements from M alpha T, let F and G be from M alpha T, then what is F minus G T of alpha? So by definition, it's nothing but F T of alpha minus G T of alpha. But this is 0 and this is 0 because the individual elements from the T-annihilator, so it must be equal to 0, right? Analogously, if you choose an element F like this and you choose an element R from Fx, then what is Rf of T of alpha? That's again by definition R of T, F of T alpha. But F of T alpha is 0, so it still becomes 0, right? So it's obviously an idea, right? So M alpha T is an ideal from the, it's an ideal in Fx. F is a field, so Fx is obviously a PID, right? So we have this to be a field, which implies Fx is a PID. So every ideal, it is generated by some unique monic polynomial. And further, you can also, think about existence of a finite degree annihilator or a finite degree element inside this ideal, because we are discussing V to be a finite dimensional vector space, right? So it has a finite degree minimal polynomial, a finite degree characteristic polynomial. The minimal and characteristic polynomial directly annihilate the linear operator T. So if they annihilate the linear operator T, then they will also annihilate the vector alpha, right? So if they annihilate the vector alpha, the minimal and the characteristic polynomial are elements of this ideal. They are finite degree. Since this has a unique monic generator, that will divide the minimal and the characteristic polynomial. So that has to be a finite degree. Right? What I'm trying to say is that M alpha T has a monic generator, say P alpha, this is P alpha, and which divides the minimal and characteristic polynomial of T. And I just explained why, right? So, no, since V is finite dimensional, because we are discussing specifically about finite dimensional vector spaces, therefore the minimal and characteristic polynomial are finite degree, right? Are of finite degree, which implies P alpha is also finite degree, right? Right. Is it clear? Further, you can also find that if alpha is not equal to 0, then the degree of P alpha is greater than 0, right? It's obvious. Okay. So having defined the T annihilator, okay, P alpha is basically called the T annihilator of alpha. This is called the T annihilator of alpha. Right? We had studied these sorts of examples, these sorts of statements in while defining T conductor, right? That the whole ideal is specifically denoted as or pronounced as a T conductor, in this case a T annihilator. But when we have some, acquirable unique monic generator of that ideal, then that monic generator is also called the T annihilator, or in that case it was called the T conductor, and so on and so forth, right? Right. So we can consider this to be the specific definition of what T annihilator of a vector is, but this is also some sort of a broader form. Okay. Okay. So let us study a theorem regarding this, which will help us understand these concepts more. Theorem. So we are considering a non-zero vector from V. So let let alpha be a non-zero vector from V, and let P alpha be its T annihilator. Let it be its T annihilator. Then we have the following. Number one, the degree of P alpha is exactly equal to the degree of the T cyclic subspace generated by alpha. Okay. Number two, if degree of P alpha is equals to K, then obviously the degree of Z alpha T is also equals to K. Then Z alpha T uh, has the following basis. We can has the following basis. The basis consists of the elements alpha, T alpha, T squared alpha, so on and so forth till T to the power K minus 1 alpha. Clear? The third is that if you restrict the operator T to the cyclic subspace Z alpha T to some linear operator, say U, that is, if U is a linear operator on Z alpha T induced by T, that is it, that is U is basically the restriction of T on this cyclic subspace, then the minimal polynomial of U is P alpha. Then the minimal polynomial of U is P alpha. Clear? So typically P alpha is the minimal polynomial of a linear operator defined on the cyclic subspace. Okay. So let us prove this. This will have some important consequence. Okay. So what we do is that we first choose a polynomial from fx. Okay. Let G be a polynomial from fx. P alpha is the T annihilator. It's obviously a polynomial, right? So we can obviously use the Euclidean algorithm on this polynomial. We can say by Euclidean algorithm, G can be written as P alpha times some Q plus R, where Q and R both are polynomials from the underlying field. R is equal to 0 or its degree is less than the quotient, which is degree of P alpha here. Clear? Now, P alpha T of alpha, this is equal to 0 by definition. That implies P alpha T times this polynomial Qt of alpha will also be 0, because both are, they are polynomials over T, so they will eventually commute. So if they commute, then we will get Qt times P alpha T of alpha, which will obviously be 0. So that means P alpha Q, this is an element of the T-annihilator of alpha, right? Okay. So if this is an element of the T-annihilator of alpha, that is exactly because they equal to 0. Therefore, GT of alpha is same as RT of alpha. Now, just look to the fact that GT of alpha must be an element of the T cyclic subspace generated by alpha, right? Now, this is this polynomial has degree less than degree of P alpha. Let degree of P alpha be is equals to K. What we are actually doing is that we are simply proving that this forms a basis. If this forms a basis, then obviously the dimension, sorry, this should be the dimension. Sorry, this should be dimension. Yeah. Then if this forms a basis, then dimension of this subspace is equal to K, and that is exactly equal to the degree of P alpha. So let degree of P alpha be equal to K. And if degree of P alpha is equals to K, then this is some linear combination. Then since R equals 0 or degree of R is less than degree of P alpha, therefore this polynomial RT alpha, sorry, this vector RT alpha is some linear combination of the vectors alpha, T squared alpha, and so on till T to the power K minus 1 alpha. Now why is it happening? Because since a degree of R is less than P alpha, so R of X is a linear combination of this form, right? So it's from the A naught alpha plus A1, sorry, A naught plus A1 alpha plus A2 alpha square, and so on till, sorry, this, let me just write it as X. Plus say here you have A to the power K minus 1, X to the power K minus 1, right? Because the degree must be less than K. So then what is RT of alpha? So it's A naught alpha plus A1 T alpha and till we have A K minus 1 T to the power K minus 1 alpha. So it's a linear combination of these elements, right? So alpha, T square alpha, and so on till T to the power K minus 1 alpha. Is it clear? But what do we have? But we have GT of alpha is equals to RT of alpha, which implies GT of alpha is a linear combination of the above vectors, right? And this typically means that because this is an arbitrary element from the T cyclic subspace generated by alpha, this arbitrary means that Z alpha T is a span of these elements, right? Span of alpha, T square alpha, so on till T to the power K minus 1. Is it clear? Now these vectors are obviously linearly independent because it's sort of like this. We can think of them. Suppose I choose a, let GT of alpha be equal to 0. Okay, or let us not talk like this. Let A naught alpha plus A1 T alpha plus A2 T squared alpha, so on, plus A K minus 1 T to the power K minus 1 alpha be equal to 0. That's, we are considering a linear relation of these elements and equating that to 0. but that typically means that it's of this form, right? Where this polynomial g of x has acquired this form. So it's a naught plus a1x and so on till ak minus 1 x to the power k minus 1. Right? But is this possible? But degree of g is less than degree of p alpha, which was considered to be k. And what was the definition of p alpha? And p alpha is the least degree polynomial which annihilates alpha, right? Annihilates alpha. Therefore, gt of alpha cannot be equal to 0, which implies the set alpha t alpha and so on till t to the power k minus 1 alpha is a linearly independent set. Therefore, z alpha t has the required basis, right? It has the required basis. And if it has the required basis, then that typically means that the dimension of z alpha t is equal to k, which was assumed to be the degree of p alpha, right? Okay. The third statement is very simple to observe, because if you consider a linear operator on z alpha t, okay, which is induced by t, then if we choose an element from G, let me just be more formal. So let this, which is induced by t, let G be a polynomial. Okay. Then what can I say about p alpha u gt of alpha? So this is clearly p alpha t gt of alpha, because u is nothing but the restriction of t to this cyclic subspace. So inside z alpha t, because u is considered to be a linear operator on z alpha t, right? And alpha is clearly inside that set, z alpha t. So u is nothing but t inside z alpha t. So we can obviously, switch between u and t inside z alpha t. So p alpha of u gt alpha is equals to p alpha t gt alpha. But obviously again they are, polynomials in t, so they will commute. So this becomes gt p alpha t of alpha, but that is equal to 0. Right? That is clearly equal to 0. So that means now if you consider this to be a vector, that is an element from z alpha t, so that's clearly an element of z alpha t, right? So that means therefore p alpha is a 0 operator. So it's clearly a 0 operator on z alpha t, right? What more can we say? If I choose another polynomial h with degree of h less than p alpha, let h be a polynomial such that degree of h is less than degree of p alpha, then observe that h u of some gt of alpha, it will obviously be of the form ht of gt of alpha, but that cannot be equal to 0, where we have chosen gt of alpha to be a non-zero vector from the z alpha t, because it will contradict the minimality of p alpha, as it will contradict the minimality of p alpha, right? So p alpha is typically the minimal polynomial on z alpha t. So it's the minimal polynomial on z alpha, or I should use it for z alpha. Clear? Now what is the important observation or important conclusion we can draw from this theorem? Observe that if you have a t cyclic vector, then what must be the minimal polynomial of t? Okay. If alpha is a T cyclic vector, then the minimal polynomial of T is nothing but the T annihilator of alpha. Is the T annihilator of alpha, and since alpha is a cyclic vector, right? Since alpha is a cyclic vector, okay, let alpha, yeah. So since alpha is a cyclic vector, therefore Z alpha T, this must be equal to the whole vector space, which implies the degree of the minimal polynomial of T equals the dimension of V, right? Which and what is the annihilating polynomial of T which equals the dimension of V? That's exactly the characteristic polynomial, right? Which implies that by the Cayley-Hamilton theorem, by the Cayley-Hamilton theorem, the minimal polynomial, and the characteristic polynomial are same. And the characteristic polynomial are. Therefore, if you have a T cyclic vector, like we have already shown that it's not a general consequence for a linear operator to have a cyclic vector. So if there exists a linear operator, sorry, if for some linear operator it has a cyclic vector, then the minimal polynomial of that operator must be equal to the characteristic polynomial of that operator. After a few moments, we will eventually show that the converse is also somewhat true. That if there exists a linear operator whose minimal and characteristic polynomials are same, then it's bound to have a cyclic vector. Okay. Okay. Now let us observe some important uh, aspects of this lecture. Okay. We consider a vector space say W, which is of dimension k. Okay. Let W be a vector space of dimension k, and let U be a linear operator on W. Okay. Such that U has a cyclic vector. U has a cyclic vector say alpha. Okay. U has a cyclic vector alpha. Now, what does theorem 1 say? If U has a cyclic vector alpha, then the cyclic subspace Z alpha T, it is generated by the set alpha, U square alpha, and so on. Sorry, here in this case the U cyclic subspace. So it will have the basis of alpha, U square alpha, so on. But Z alpha T is exactly equal to W here. So W will have the basis alpha, U alpha, and so on till U to the power k minus alpha. Therefore, W is spanned by alpha, U square alpha, and so on till U to the power k minus 1 alpha. Okay. And just we have observed that the minimal polynomial of this linear operator U must equal the characteristic polynomial. And the minimal polynomial also from the previous theorem is exactly the T annihilator of alpha. And the T annihilator of alpha equals the minimal polynomial, sorry, and the U annihilator of alpha is exactly equal to the minimal polynomial of U, which must be equal to the characteristic polynomial of U. That is the degree of the U annihilator is obviously equal to K, right? Now what we do is that we consider a standard ordered basis of W, or I shouldn't use the term standard, an ordered basis of W. Okay. Let B be the set of vectors alpha 1, alpha 2 till alpha k, be a ordered basis of W, ordered basis of W, and how we have chosen these vectors, okay, such that we have chosen these vectors alpha I to be the I minus 1th image of alpha under U, okay, okay. Then having chosen these vectors like this, one obvious conclusion we can draw is that U of alpha I is exactly equal to alpha I plus 1, or let me just break down this observation a bit, okay. Then what is alpha 1? So alpha 1 is U0 of alpha, but U0 is obviously the identity operator. It's always a conventional assumption. So that's exactly equal to alpha, right? Then what is U of alpha? Okay. Or let me say what is U of alpha 1? Then U of alpha 1, so U of alpha 1 is basically U of alpha, but U of alpha from this definition, so U of alpha, that means it's U to the power 2 minus 1 of alpha, so that's exactly equal to alpha 2, right? Then we have got that alpha 1 is alpha and U of alpha 1 is alpha 2, that is U of alpha is alpha 2. What is U of alpha 2? So U of alpha 2, how can we find it? That, see, alpha 2 is exactly equal to U of alpha, so that means U of alpha 2 is U square of alpha, but U square of alpha is alpha 3 from this definition, so it's alpha 3, right? If you proceed like this, you will eventually get that what is U, what can we say about U of alpha k minus 1? Okay, what is U of alpha k minus 1? So U of alpha k minus 1 is nothing but alpha k, right? Right? U of alpha k minus 1 is nothing but alpha k, right? So if U of alpha k minus 1 is equals to alpha k, then that's basically equal to, so U of alpha k minus 1 is nothing but U to the power k minus 1 alpha, right? Right. So one obvious observation is that this basis is typically of the form alpha, U square alpha, and so on till U to the power k minus 1 of alpha. So therefore, observe that U alpha I is nothing but alpha I plus 1 for all I is equals to 1 to k minus 1, right? What can we say about U alpha k? What can we say about U alpha k? Now, one obvious observation is that U alpha k cannot choose a value other than one of these alpha 1s to alpha k, right? Because we have already constructed the format of a basis. We have already have enough elements as there in the basis. But that's not quite a statement I would speak. Observe that let P alpha be of this form. So it's of the form C0 plus C1x plus C2x square and so on till Ck minus 1 x to the power k minus 1 plus x to the power k, since it's a monic polynomial obviously. Therefore P alpha of U of alpha is equal to 0, right? So that implies C0 alpha plus C1 U alpha and so on till Ck minus 1 Uk minus 1 alpha plus so here you have U to the power k alpha. This is equal to 0. But then U to the power k alpha, this can be written as minus C0 alpha minus C1 U alpha minus C2 U square alpha and so on till minus we have C to the power Ck minus 1 U to the power k minus 1 alpha, right? Right. But that implies uk alpha. Now what is so alpha is basically alpha 1, right? So it's minus c0 alpha 1. U alpha is alpha 2, so it's minus c1 alpha 2, minus c2 alpha 3, so on till minus ck minus 1 alpha k, right? Is it clear? But what is u to the power k alpha from the observation we were speaking? So u to the power k alpha is nothing but u of alpha k, right? So it's exactly equal to minus c0 alpha 1 minus c1 alpha 2, so until minus ck minus 1 alpha k, right? Is it clear? Right. Okay. So therefore, the statement which I was going to write, that therefore we have u of alpha I to be equals to alpha I plus 1 for all I is equals to 1 to k. This is statement 1. And u of alpha k is equals to minus c0 alpha 1 minus c1 alpha 2 and so on till minus ck minus 1 alpha k, where the minimal polynomial has this form. So it's c0 plus c1x and so on till ck minus 1 x to the power k minus 1 plus c plus x to the power k, right? But these elements alpha 1 alpha 2 till alpha k, they form an ordered basis of w. Therefore what can I say about the coordinate matrix of u alpha I when say I is equals to 1 to k minus 1? So see this vector alpha I, it's expressed with a linear combination of the basis vectors alpha 1 till alpha k by having the coefficient 1, positive 1, with the basis element alpha I plus 1, and all the other coefficients are 0, right? So it's just 0 till then you have 1, then again you continue with 0, and this one is attained at the I plus 1th position, right? That is what is u of the coordinate matrix of u of alpha 2 with respect to the basis. So it's basically 0 0 1 and all the rest of the elements are 0. What can we say about the coordinate matrix of u alpha k with respect to the given basis alpha 1 till alpha k? So it's simply these elements minus c0 minus c1 minus k minus 1, that is basically the negative of all the k minus 1 coefficients in accordance with their existence in the polynomial p alpha. So it's minus c0 minus c1 and so on till minus c k minus 1, right? Therefore so there are obviously k elements. There are k elements here and there are k elements in each of these columns. Then what is the matrix of u with respect to v? Like just arrange these column vectors. This was previously studied in the matrix of a linear transformation, right? Just arrange these coordinate vectors or these coordinate matrices along the ordered, in accordance with the ordered basis. That is the coordinate matrix of u alpha 1, the coordinate matrix of u alpha 2. So as the matrix, the coordinate matrix of u alpha 1, the coordinate matrix of u alpha 2, and so on till the coordinate matrix of u alpha k. So that's of this form, right? So it's of the form 0 1 0, all are 0, 0 0 1 and all are 0. Then you have 0 0 0 1, then all are 0, and so on till you have 0 0 0, the last element is 1. Then you have minus c0 minus c1 minus c2 till here you have minus ck minus 1, right? This is the matrix representation you get, right? This is called the companion matrix of for the monic polynomial p alpha. This is called the companion matrix for the monic polynomial p alpha. Clear? Now my question is, what should be the general determinant of a K cross K companion matrix? What is the determinant of a K cross K companion matrix? Let us try and find it out. Okay. An obvious procedure we would follow, since we are working with a K cross K companion matrix, I'll prefer following the principle of mathematical induction, let's say. Okay. So we induct on the dimension of the matrix. On the dimension of the matrix. Now there is nothing to talk about a one-dimensional matrix. Let us start with a two-dimensional matrix. Let A be a 2 cross 2 companion matrix. Companion matrix for a monic polynomial. For a monic polynomial, say P of x, which is obviously, so it will have three elements. So let them be C0 plus C1x plus C2x square. Okay. Sorry. It will be of plus x square. Right. So what should be A? So A is clearly of this form. Right? So it's 0, 1, and then minus C0 minus C1. What is the determinant of A? Sorry, what is the characteristic polynomial of A? So it's say xi minus A. So it's obviously x C0 minus 1, and here you have x plus C1. So it's x into x plus C1 plus C0, right, which is equals to x square plus C1x plus C0, right? And you're getting a relation. Okay. Now let A be a K cross K companion matrix. Now we are not considering any polynomial as such. We are just giving a K cross K form of a, or rather let us say we consider a general form of a companion matrix. Okay. Let the general form, obviously in accordance with the way we have got a companion matrix, so let the general form of a companion matrix be given, or let us just use a symbol for the companion matrix we had got during the study of our observation. So let this be denoted as star. Okay. B star. Okay. Let the characteristic polynomial of a K cross K companion matrix be of the form x to the power k plus ck minus 1, x to the power k minus 1 plus ck minus 2, x to the power k minus 2, and so on and so forth till c1x plus c0. And obviously these c0, c1 are all appearing in the companion matrix, right? c0, c1, ck minus 1 all appearing in the last column of the companion matrix. Okay, we consider this to be the characteristic polynomial of a K cross K companion matrix. We need to show that the characteristic polynomial of the K plus 1 cross K plus 1 companion matrix will be similar, right? Will be analogous, I would say. Consider a K plus 1 cross K plus 1 companion matrix of the form star, and let it be denoted as A. Okay, so A is typically of this form, right? So it's of the form 0, 1, 0, 0, and so on to 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, so on. You'll have 0, 0, 0, 1, and here you have minus C0, minus C1, minus C2, so on and so forth till minus Ck, right? The last element in the last column here will be minus Ck because we are considering a k plus 1 cross k plus 1 comparison. You can obviously compare this with this form star. You'll get your answer. Why we have used minus Ck. Okay. Now what can we say about this polynomial xi minus a? Right. So what's the form of this? So it will obviously have the form. So if you have x here, so you will have x around the diagonal elements, right? Here you have x plus ck. Right? All these elements are 0, and these elements become c0, c1, c2 till this. Here you have so you had 1, right? So here you become minus 1. Here you have a minus 1. Here you have a minus 1, and all the other elements are 0, right? And here in the last column you have a minus 1 here again, right? This is the form we will get. We consider the determinant of this with respect to the first column, let's say. So let me use the determinant notation, right? I have wrongly used the matrix notation. So yeah, this is k. Okay, then expanding about first row, what do you get? You get x times the determinant of this polynomial, right? So you get x. So you have x till, yeah, right? Here you have your x plus ck, right? And then everywhere you have 0 here. Here you have minus 1. Here you have minus 1. Here you have a minus 1 again. Here you have c1, c2 till this, and here you have 0, right? So this you get plus 1 times you get another matrix, which will obviously be the cofactor of 1. So you just need to omit. You just need to omit this. Sorry. You just need to omit this row and this column. Right? This is what you will get. Right. Okay. Let that matrix, for this moment we consider this to be, let's say, bx. Okay. Now this is a k cross k dimensional companion matrix, characteristic polynomial. So this is the characteristic polynomial of a k cross k dimensional companion matrix. What is the only difference here with respect to the general form which we had considered? Here is that the index has shifted by 1, nothing else. Right? Here C0 has become C1, C1 has become C2, and so on and so forth. Ck minus 1 has become Ck. So what should be the determinant of this by our induction hypothesis? Right? Now let us assume this matrix, this determinant, to be some Cx. Okay. Then by induction hypothesis, so just we need to replace k with k plus 1 because we obviously the index have just shifted by 1. By induction hypothesis, Ck has this form, right? So it should have the form. Okay, yeah. So it should have the form. So yeah, what can we observe from here? Yeah, we have kx values, and the index of c has shifted by 1. Yeah, so we have here ck, right? Sorry, xk plus ck x to the power k minus 1 plus ck minus 1 x to the power k minus 2, and so on till we have c2x plus c1, right? Right. Okay. Then what is x times cx? Therefore, x times cx is basically x to the power k plus 1 plus ck x to the power k plus ck minus 1 x to the power k minus 1, and so on till c2x square plus c1x. right? So this part of the determinant is done, right? This part of the determinant is done, and this part is also very easy to observe, because what is the form of Bx? The form of Bx is typically of this form, right? Observe that it's of this form. So we have 0, 0 till C0. The C1 row has vanished, and the first column has vanished, right? Sorry, yeah, the C1 row has vanished and the first column has vanished. So you have -1, 0, 0. Then you have x -1, 0 until 0. Then you have, so let me just one more. So it's x -1, 0 till 0, correct? Oh, yeah. And then you have C2 here, and so on till here you have x plus ck. Right? Now expanding along first row. Expanding along first row. Now, obviously, the expand, if we expand this along the first row, then we get C0 times the determinant of this matrix, right? So it's -1, -1, -1, and so on, right? So, yeah, it will go on like this till you have -1 here, because this row vanishes, right? And so because this column vanishes and this row vanishes, right? So you will start with -1, you will end with -1 here, right? And then you have x here, and so on. But these are the super diagonal elements, right? What should be the determinant of this? The product of the diagonal elements. It's a upper triangular matrix, right? Therefore, it's C0 times 1, right? It's typically C0. Let me write it in a bit more way. Observe that if this is a odd dimension matrix, then the sign allotted to C0 will be plus, right? And the minor of C0 will be then even dimension, because if this is a k dimension matrix, then you will get a k minus 1 dimension matrix. So if k is odd, k minus 1 is even. So if this complete matrix is odd dimensional matrix, then the this matrix is typically an even dimensional matrix. If it is an even dimensional matrix, then there are even number of -1s in the diagonal. So that typically makes it plus C0 times -1 to the some even power. So that's exactly C0, right? What can we say about if it's an even dimensional matrix? If it's an even dimensional matrix, then the sign allotted to C0 will be minus C0 times determinant of, will have the same matrix, right? -1, -1, -1 till -1. You have x here, you have x here. But in this case, there are odd number of -1s, because this is an odd dimensional matrix. So you have odd number of -1s. So you can pair every -1 excluding just one of them. So it's typically equal to minus C0 times -1 to the power some even power times minus, right? Because then it will make odd number of -1s. That's exactly again C0. So in either case, you will get C0. Right? Therefore, what is the characteristic polynomial of xi minus? What is the characteristic polynomial of a? So it's typically coming out to be of the form x to the power k plus 1 plus ck x to the power k. This we had already acquired, right? Plus c2x square plus c1x, and then we just need to add 1 times c0 plus c0, because that was a form, right? Yeah. Plus 1 times bx, and bx has come out to be c0, right? And therefore that's exactly what we wanted by the induction hypothesis. Therefore, by induction, the characteristic polynomial of a companion matrix of the form star is, so it's x to the power k plus ck minus 1, x to the power k minus 1, and so on and so forth till c1x plus c0, right? Right? Okay. Is it clear? Now we come back to a very important theorem, or rather what we were discussing, that the minimal, equality of the minimal and characteristic polynomial. We will get something from this theorem. Theorem says that if U is a linear operator on a finite dimensional vector space W, then U has a cyclic vector. Then U has a cyclic vector if and only if there exists some ordered basis for W in which U is represented as the as a companion matrix, or I should use the term as the companion matrix, of its minimal polynomial. Okay, a quick proof to this. One thing which we have obviously observed is that, because the observation before this calculating the characteristic polynomial of a companion matrix was simply that if you have a linear operator defined on a finite dimensional vector space which has a cyclic vector, then it surely has this representation. It has a basis. We represented the elements of the basis as alpha 1, alpha 2 till alpha k, and we consider this linear operator U such that U of k minus 1 alpha is alpha k. Right? This is what we did, right? Just go back once. Yeah. So we have alpha is equal to U to the power I minus 1 alpha. This is what we did. Right? So therefore, if U has a cyclic vector, then U can be represented. Just we have, this is trivial from the observation we just had. So U can be represented as the matrix, as the companion matrix of its minimal polynomial. What about the converse? What can we say about the converse? Observe that if you have some ordered basis, let B equals to U1, U2 till UK be an ordered basis of W such that the matrix of U with respect to W is of this form. So it's 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, so on, 1. And then here you have minus C0, minus C1, so on till minus Ck minus 1, where you can consider the minimal polynomial as this. Right? So it's C0 plus C1x plus x to the power k. Right? But then what can you say about the images? Sorry, this is not UK. I'm very sorry again. This should be chosen to be some alpha values. Yeah, alpha 1, alpha 2 till alpha k. Sorry. But then what is U of alpha 1? From this, what we can say? Clearly, U of alpha 1 is equals to alpha 2. Right? Then U of alpha 2 is equals to alpha 3. But what does it mean by U of alpha 1 to be alpha 2? Then that basically means, so U of alpha 2 is equals to alpha 3. This means U square of alpha 1 is alpha 3. Then U of alpha 3 is alpha 4. But that means U cube of alpha 1 is alpha 4. Right? And so on. We can continue till we have U of alpha k minus 1 to be alpha k, but U of alpha k minus nothing but U to the power k minus 1 alpha, and that's exactly equal to alpha k. Therefore alpha 1 u alpha 1, u square alpha 1, and so on till, so this should be alpha 1, correct. Till u to the power k minus 1 alpha 1 spans w. But that means w is nothing but z alpha 1 u. So that means alpha 1 is a cyclic vector for you, right? I guess this was a very easy sort of theorem, but the important one is its corollary. The corollary. Okay. So if A is a companion matrix of a monic polynomial P, then P is both the minimal and characteristic polynomial of A. Okay, how can we conclude this? Observe that we already have the form of the characteristic polynomial of A. So if I choose A to be a k cross k characteristic polynomial, sorry, k cross k companion matrix, let A be a k cross k companion matrix of the form star, but obviously this polynomial P abides by the form of star, then we have the characteristic polynomial of A to be x to the power k plus ck minus 1 x to the power k minus 1, so on till you have c1x plus c0, right? Okay, what can you say about the minimal polynomial? That's my question. Obviously this is a k degree polynomial which annihilates the matrices. We just need to just abide by all these studies we had in terms of a matrix, but that's quite easy, because observe that if I consider this matrix A in this form, that if I consider, say, let U be a linear operator on the vector space Rk, or let's say a field K, that entries of A are from this field, such that if B is the standard ordered basis, we are considering the standard ordered basis of Rk, then the matrix representation of U with respect to the standard order basis is this companion matrix. But doesn't that immediately mean that E1 is the cyclic vector of for U, right? Then use theorem 2. Therefore, by theorem 2, you can just validate each of these statements. Okay. Then by theorem 2, P is the minimal polynomial of U. And what do we get by theorem 1? Or the previous theorem? Let this be theorem 2. Let this be theorem 2. And the first theorem we studied, where was it? Yeah, I guess this one. Let this be theorem. Okay. So from theorem 2 we get P to be a minimal polynomial. You can also conclude P is a minimal polynomial by theorem 1 itself. And by theorem 1, the degree of P must be equal to K, which is exactly equal to the characteristic polynomial of degree of the characteristic polynomial of A, right? So P is the minimal polynomial of U, which means P is the minimal polynomial of A, right? Therefore, the minimal polynomial, just validate these statements from here to here. It will be quite easy. Just study theorem 1 and theorem 2 properly. Minimal polynomial of A equals the characteristic polynomial of. Is it clear? Okay. So our next goal will be to try and decompose a given finite dimensional vector space into these T cyclic subspaces generated by non-zero vectors of V, okay, which is typically called the cyclic decomposition theorem, and it's one of the deep theorems of linear algebra. Okay. In the next lecture, we will be coming to the statement of cyclic decomposition theorem thoroughly through steps which will help us understand better this first the statement of the cyclic decomposition theorem. We won't be immediately proving it in the next lecture because proving the cyclic decomposition theorem requires a bit of work, and those works which we will be doing in the next lecture. And then in the third lecture, or that is the lecture after the next lecture, we will be proving the cyclic decomposition theorem. Okay. So meet you guys in the next lecture.